Dr. Saurav Chakrabarti, working as an associate professor in the computer science group at the Chennai Mathematical Institute, Tamil Nadu. Before joining Chennai Mathematical Institute, he was a postdoctorate at the Algorithms and Complexity Department of CWI, Amsterdam, Netherlands. He was a postdoctorate at the Computer Science Department of Technion, Israel. He was awarded PhD in Computer Science from University of Chicago. His area of research is theoretical computer science. His focus has been in the classical and quantum complexity of Boolean functions, including property testing, sensitivity, block sensitivity of Boolean functions, and quantum database search in electronic commerce, in graph algorithms, and in coding theory. He has published several research papers in both national and international journals.
Welcome to the UGC lecture series in computer science, and the topic is algorithms. So, today we will be looking at one more kind of sorting algorithm called Heap Sort. We have seen quite a number of sorting algorithms in the last few lectures. Today we will be seeing one more of those kinds. So, the problem at hand is we have been given a set of integers and we want to sort this set of integers in an ascending order. Note that here the integers plays no particular role, is all that matters is this set of elements has a total ordering. In the case of integers, we have a total ordering, and that is why we have used that one as an example. So, for example, if S is this set 1, 4, 2, 10, 5, 8, 15, 13, 7, 8 and 1, and we want to sort the elements in this set S in an ascending order. Thus, we want to have an output something like this, which is 1, 1, 2, 4, 5, 7, 8, 8, 10, 13 and 15. Now, sorting is one of the most studied algorithms in whole of computer science, and in fact, there is a huge number of sorting algorithms. Each of them have their own plus points and own minus points. Here are a collection of them. This set is by no means complete. Out of this set, we have seen 3 algorithms till now. We have seen insertion sort, quick sort and merge sort, and today we will be going to look at heap sort. So, let us review all the 3 sorts that we have seen. So, first of all, in the case of insertion sort, the idea was simple. So, we wanted to maintain a sorted list T. So, what we do is that we start with an empty list, which is of course sorted because it is empty, and then one by one we take elements from this set S and we insert it in the sorted list T in the right place. And we have also seen that this T one can maintain in the same place where the set S is stored. Thus, we do not need to use any additional space to maintain this set T. So, here is the pseudo code of our insertion sort. It is relatively simple, and all it does is it maintains a sorted list. So, it rather uses a space of itself, the space where the S is stored, a part of it is used to maintain T, which is the sorted list. The summary of the insertion sort was that it does give the right output, that is it correctly sorts the list S. The runtime or the number of steps made by this insertion sort was something of the form n square plus 3 n by 2, and the space complexity was actually constant, meaning we have not used any additional space, but we of course need some space to maintain our registers, like when we say for all I equals to 1 to n, we have to maintain that I, and for that we need log n bits of memory. So, the space complexity is log n. The natural question to ask was, can we improve the running time beyond n square while maintaining the space complexity log n. And we got the answer partially in our quick sort. The quick sort is also a very simple algorithm. So, we pick an element x from this set S and we keep all the elements which are less than x to the left and all the elements greater than x to the right, and then we recursively sort all the elements which are left of x and then recursively sort all the elements that are right of x. We also saw a variant of this quick sort where this algorithm of splitting this whole set S into less than x and greater than x can be done in place. That means, we can use the same space that is used by the set S to do the splitting. In other words, we do not need any additional space for maintaining what all the set of elements which are less than x or what are the set of elements that are greater than x. So, here again we have the pseudocode of our quick sort, and again it was not very hard. We just split this set x into two parts, R and L. R contains all the elements which are less than x and L contains all the elements that are greater than x, and then we recursively sort L and then we output x and we recursively sort. The summary of this quick sort was, as such it does not seem to be doing any better than insertion sort. In other words, it has time complexity around n square and space complexity log n. But we also saw that if instead of picking a particular x, in this case the first element of the x, if we pick a random element from this set S, in that case we have a expected running time, or in other words the average running time will become something of the form n log n. So, clearly n log n is better than n square, and so it was better than insertion sort. The next question to ask is, can we do better than n square in the case of worst case running time? Although quick sort achieved n log n in the case of the average case running time, but in the case of worst case running time it still did n square. And to do that, we looked at the merge sort. The merge sort, we just split this set into two equal size sets and then we recursively sort the two sets, but now we have two equal size sets and there is no ordering across these two sets. So, once we have these two sorted half sets, we have to merge these two sets into one properly sorted set. So, this algorithm was also simple, and clearly the pseudocode shows that it is kind of very simple. You just split it up into two halves, sort them out recursively and then merge them. And this algorithm merge sort seems to be doing really well. In other words, it had time complexity only 2 n log n. So, it is the worst case time complexity, but the space complexity was order n. So, while in quick sort and insertion sort the space complexity was very low, which is log n, in the case of merge sort the worst case space complexity is n. But at the same time, in the case of merge sort the worst case time complexity is n log n, which is significantly better than the n square that we get from the quick sort and insertion sort. A natural question to ask is that, can we get the best of the both worlds, or in other words, can we obtain an algorithm with running time n log n and space complexity log n? This is where we have to come up with a new algorithm which we call heap sort. Now, to start with the heap sort, we have to understand a new data structure called heap. Heap is one of the important data structures that is used in many things including this particular sorting algorithm. So, what is a heap? Heap is just a way of organizing a set of elements or a data on a binary tree or a complete binary tree or a balanced binary tree, such that some properties is maintained, such that each node of the tree contains only one element and exactly one element of this set. And the other thing is that every node must have an element which is less than the element of its child, or in other words, for every node the element on the child node must be more than or equal to the element on itself. Let us see a simple example. Say we have this set S, which is 1, 4, 10, 10, S 4, 8, 15, 13, 7, 12, 9 and 5. Now, we want to store them. So, one way of storing it is this. So, this is a heap. Why the heap? Note that it is a binary tree. That means, every node has exactly 2 children. Now, for people who are not familiar with this notion of children, this looks like a tree, like a family tree. So, the top element is what is known as the root. Now, each of its neighbors, anything that comes below it are the children. So, here this node and this node are the children of this node. Similarly, the node 9 and 15 is the children of 5 and so on. The other property of this heap, this tree, is that this tree is balanced. In other words, we can have some tree like this, that I have a tree, I have 2 nodes and root, and we have 2 children, and this children has say 2 sub children, and then this children has 1 children. This is also a tree, a binary tree, because every node has 2 children, at most 2 children. But the fact is that it is not balanced, because while distance from this node to this node is 4, 1, 2, 3, 4, but distance from this to this is 1. We call it balanced if the distance from any of the bottommost nodes, or what we call as the leaf nodes, to the root is almost same across the tree. So, that means, the distance from this node 10 to 1 is 4, whereas distance from 15 to 1 is just 3. 4 and 3 just differs in 1. And also it is balanced that we make sure that always the left hand side gets filled up quickly. So, we cannot have something like this, that so this is a tree and we cannot have this. This is, although it is a binary tree and it sounds to be balanced, but this is not good for us, because we could have added another node here which is not there, and so this is not good for us. So, this is the one example of a balanced binary tree. Now, why is it a heap? It should also have the other property. Note that each node contains one number, the numbers coming from the set S, and at the same time this heap has the property that, take any node, say 9, the 9 is less than its parent 5 and 9 is greater than its children 10, or say take this node 4, 4 is greater than or equal to its parent 4 and less than its children 7 and 8. So, this structure or this example is a heap, and this kind of data structure will be used for designing our heap sort. We will take a short break now. After the break, we will look at how to use this data structure for designing the heap sort algorithm. Welcome back after the break. So, before the break we were seeing the data structure heap. So, here was the example of a set S and how one can arrange it in this heap form. Now, the heap has a few properties. For example, the root element or the element that is stored in the root is always the smallest element in this set. Why is it so? Because the parent must contain a number that is always lesser than the child. Thus, the root must contain a number that is lesser than every descendant or child or grandchild or any such things of the root. The other thing is the height of the tree. The height of the tree is log n to the base 2 plus 1. Because the tree is almost balanced, that is why we can arrange it in such a way that the tree comes to the height comes to log n plus 1 to the base 2. Now, just like in the case of say a array or a linked list, which are data structures, two important properties to note is that we want to check how to store a heap. Like in the case of an array, it is very easy to store an array. You can store it an array in a random access memory model or RAM model. Similarly, in the case of heap, and heap can be stored in an array. The reason is that if I have the parent is the ith node, then the parent of the ith node is exactly equals to I by 2, the integer which is just less than I by 2. And in the case of the child, if I is the ith node, then the left child is given by twice I, whereas the right child is given by twice I plus 1. Thus, we can store an heap in an array in such a way that if we are accessing a particular node, we know that where the parent node will be or the child nodes will be, and that can be easily accessed in a random access memory model. So, storing an heap can be done in an array. For example, here say if I number this one as this is the first node, this is the second node, this is the third node, this is the fourth node, this is the fifth node, this is the sixth node, this is the seventh node, this is the eighth node, this is ninth node, 10, 11 and 12. Look at this example, the sixth node. Now, what is the child of the sixth node? The child of the sixth node will be twice I, which is 12, and what will be parent of the sixth node? It will be 6 by 2, which is 3, or let us say 5. When we take the fifth node, then the parent of the fifth node will be 5 by 2 floor, which is 2, and the two children will be 2 times 5, which is 10, and 2 times 5 plus 1 is 11. So, this is an example how we can quickly go from one node to its parent and child. The indices are so well designed. Now, let us talk about adding an element in the heap. Just in the case of array or in insertion or in linked list, where we have to work hard for inserting an element in an array or something like that, one important aspect of any data structure is how to include a new element in this data structure. So, for example, say here is a set S and here is the heap that represents this set S, and I want to add a new element, say for that matter 2. Now, where do I insert this element 2? The idea is that we just put 2 as the child of the whatever thing was incomplete. For example, here we make 2 to be the child of 9. But now, this although this is a balanced binary tree, this tree now does not satisfy the heap property, because this age is violated. In the other words, the parent of 2 is 9, which is bigger than 2, which should not be the case. And thus, what we do is that we will just swap 2 and 9. We will send 9 down and send 2. Note that this number 9 was such that this 9 was always less than 10 and 2 was less than 9. So, 2 will anyway be less than 10. So, we do not have to worry about the other child. Similarly, again we see that one more edge is violated, which is 2 and 5, and again we can swap those two elements to get 2 and 5, and now we see that there is no violation, and thus this is a valid heap arrangement for this set S. So, in other words, I can add an element to this set in just log n plus 1 steps. Log n plus 1 is because we might have to go through the whole path to the root. The other important thing is that if I have n elements, then what we can do is that we can construct a heap for all the elements using just n log n steps. It is just in the same way as creating a sorted list. So, we take an element and we insert it in this heap, and we keep on doing it for the n elements, and each of the insertion will take log n steps. So, after n log n steps we will have inserted the whole element in the heap. Now that we have been able to create the heap structure for all the elements, the next important thing is the removing of the element. More importantly, in our case what we need is an extract min, which is that we have been given a heap structure for this set and we want to extract the minimum out of this set. Now, note that here the minimum is clearly on the root. So, extracting the min is very easy, we just remove the 1 and take it away. But the problem is that then the heap structure is disturbed. So, how do we manage to solve it? Again, what we do is that we take one of the last nodes and put it in the root. For example, here we take 9 and put it in the root. Once we put it in the root, then there we see that there are some edges violated. For example, 9 and 4 is violated and 9 and 2 is violated, because 9 is greater than 4 and greater than 2, whereas that cannot be. So, in that case we look at both the child of 9 and then we see which of these two childs are the smallest. In this case 2 is the smallest, and so this edge we just swap 9 and 2, and after we swap 9 and 2 we can again swap 9 and 5 and so on, and we will end up getting the heap structure back. So, thus one can extract one element from the heap while maintaining the heap structure in log n plus 1 steps, and this is where the interesting thing happens. So, given a set S arranged in a heap structure, we can one by one take elements out of this heap, the minimum out of the heap. Every time we take a minimum out of the heap, it will take log n steps and the heap goes down by 1, and but we still maintain the heap structure. Thus, if we have been given a set S arranged in a heap structure, then in less than something like 2 n log n steps we will be able to order the whole set S. So, you take the first time you ask give the minimum is extracted, we are left with some other heap, then we take the okay give the minimum of the next heap. Note that again that will be the second minimum of the whole set, and we again extract it, and that will take another log n, and again we have a heap structure. Then we will ask another third minimum, and so by doing so we will be able to sort the elements in less than 2 n log n. So, thus now we have the idea of the heap sort. So, we have been given the set S. The first step is arrange the elements in an heap formation and then use this heap to sort the elements. So, here is the pseudocode. I mean is very simple. We take one by one element and we insert it in this empty heap initially, and then we extract one by one. Note that this is very similar to the insertion sort. Here we are maintaining the heap structure, there we are just maintaining a sorted list. The crucial part of this whole thing is that in the case of sorted list, insertion was taking order n steps, whereas in the case of heap, insertion requires order log n steps, and that is where we make the advantage of using the heap structure. So, thus we can say that the heap sort will correctly sort the elements of the set. The runtime will be something like 3 n log n, 1 n log n for formation of the heap and twice n log n for using that heap to get the sorted list. The space complexity is n, but just in the case of insertion sort, the same space as S to maintain the heap, and this is where we need the how the heap is stored. The heap is stored in an random access memory model, which is an array, and thus one can use that structure to store the heap in the same place where the set S is stored, and thus we will not need any additional space. After that we have the heap sort runtime 3 log n, whereas the space complexity will be log n. This is almost as good as we can think of, because we have combined the best of both the worlds. So, for example, in the case of comparison with merge sort and quick sort, what we see is that while in the case of quick sort the expected runtime was n log n, the worst case runtime was around n square, but the space complexity was log n. In the case of merge sort, the worst case complexity went down to twice n log n, but the space complexity we could not have a control of it and it went up to n. And in the case of the heap sort, we have the worst case complexity thrice n log n, whereas the space complexity is just log n. So, we leave you with some questions. First of all, can we use better data structure to obtain some better algorithm? And if not, why would one any day use merge sort or insertion sort or heap quick sort instead of heap sort, which seems to have a better parameter than both of them? We will talk about these two questions in the next lecture. So, to summarize, today we looked at the heap sort algorithm for sorting. So, this kind of combines the best of both worlds of quick sort and merge sort. So, with this we end our lecture. In the next lecture, we will try to see how to compare between all these various sorting algorithms. Thank you.